Hello, welcome back to Educator.com and welcome back to Biochemistry. So today's topic, we're going to talk about phosphoryl group transfers. We've been talking about how you take some endergonic reaction and you couple it with an exergonic reaction like the hydrolysis of ATP to actually drive the endergonic reaction forward. Well, we're going to talk about how that actually happens. What is it that takes place? What is it that makes this possible? So let's go ahead and get started. Okay. So let's go ahead and recap one more time. I know that you've heard this several times already. I hope you're not getting sick of it, but it is important to hear things several times before it actually sinks in and you start to think about it in the background regularly. So that's okay, we'll go ahead and keep it in black. So we saw that the coupling of ATP hydrolysis, to the phosphorylation of glucose, allowed an otherwise endergonic reaction an endergonic phosphorylation, because that's what's happening, an endergonic phosphorylation to proceed exergonically. Right? We had GLC plus Pi going to G6P plus H2O. And of course we had the ATP hydrolysis, which was ATP plus H2O going to ADP plus the Pi. And when we combined that, we ended up with an alternate pathway, GLC plus ATP going to ADP plus, actually I should write the G6P first. Going to the glucose 6-phosphate plus our ADP. Okay. Now, the glucose is activated. And ready for further reactions. Okay, so this is what ATP generally does. Now, this is what ATP generally does. Excuse me. Namely, it provides its energy, that negative 30.5 that it has, it provides this energy by transferring a phosphoryl group. A phosphoryl, a pyrophosphoryl, or an adenylyl group. Okay, this is what ATP generally does. It provides its energy by transferring either a phosphoryl, like in this case, a pyrophosphoryl, or an adenylyl group to a substrate molecule, let me see. Giving, you know what, I'll talk about the raising of the energy a little bit later. So a pyrophosphoryl or an adenylyl group to a substrate for further reaction. Okay. And often the next reaction is displacement of the group that was transferred. Group that was transferred. So what happens is the following. We have glucose, which is a specific molecule, and in the process of phosphorylating it, what it does is now that a phosphoryl group is attached to this glucose, now the energy content, it's invested energy into this glucose molecule. It's raised its free energy content. So now this molecule can go on to react further with something else, and now the thing that it's going to end up reacting to, now there's a bigger difference. Now it's raised the energy content, so now that molecule can react and give away its free energy. That's what it's doing. If somebody only has $5 but they need to buy something, I can come along and give them $100, and now they have $105. They can do the thing that they wanted to do. Whereas before they couldn't do it with the $5, they didn't have enough. That's all that's happening. ATP, by transferring its phosphoryl group, in the act of putting on a phosphoryl group on that molecule, in this case on glucose, it's raised the energy content of the glucose. Now the glucose can go and do whatever it wants. It's invested money into the glucose. That's what ATP does, and this is what it generally does. And usually what happens, the next step of the reaction, more often than not, or maybe a couple of steps further down the line in a metabolic pathway, is that this phosphoryl group that's now attached to this molecule is going to end up being displaced. So literally what you're doing is you're taking a molecule that often doesn't have a very good leaving group. By attaching a phosphoryl to it, you've created a good leaving group. Good leaving groups tend to, well, they want to leave, so it's going to pull the reaction forward. Its energy content has been increased, so now in a reaction it's going to have a negative delta G when it reacts further. Hopefully that makes sense, but we'll see more of it here. Okay. So let's see what's going on. Let's do an example of this, actually, and then I think, of course, it'll make sense. Let's do this in blue. Okay, so the example, let's go ahead and do the following reaction. Let's take glutamate, and we are going to ATP ADP plus glutamate plus ammonia, I should say. Those are the reactants. And we are going to form glutamine. Okay, so let's take a look at this reaction. We're going to take glutamate and ammonia, and we're going to produce glutamine. And ATP is going to actually drive this reaction. The hydrolysis of ATP is going to drive this reaction. But we know that when we say that, we don't mean that ATP is actually hydrolyzed. There's no hydrolysis taking place. ATP is going to invest glutamate with a certain amount of energy, allowing it to turn into glutamine more easily because it wouldn't otherwise happen. Here is how it takes place. So let's go ahead and draw our glutamate molecule. We have NCC. I'll just write OO minus here, and I'll go ahead and put that there. We have CH2, CH2, I'll go ahead and do it this way. So this is our glutamate molecule. So now let me go ahead and draw the same thing that I just drew. So we have ADP plus PI, and we have adenosine triphosphate there. Now glutamine is going to be this. Let me just write NH3 in red. I might as well take advantage of the fact that I've got these multiple colors here. I often get so wrapped up in it that I forget that I can do that. NH3 plus, that's COO minus, that's CH2, that's CH2, that's going to be COO, and now this ammonia is going to end up being attached here to form this, to form glutamine. So here's what's going on. Let's do this. Well, that's fine. I'll just go. Let's go ahead and do this in red. Now, it appears as though this reaction just takes place in one step. Just takes place in one step. But it's actually two. And this will demonstrate how ATP does what it does. It's actually 2. So the first step is the following. We have the N. Should I do it on the next page or should I do it on... Yeah, it's okay. I can do it on this page. It's not a problem. Let me go ahead and go back to blue here. So we have NCC. I've got CH2, CH2, COO minus. The first step is the ATP. Boy, all these letters, oh my God, I think that's the most frustrating aspect of biochemistry is just the abbreviations, the letters. Woo, it's crazy. BP, this is COO minus. Let me just go ahead and make sure I have the structures correct here. So we have H3N, this is C, this is COO minus, so we have CH2, we have CH2, and we have COOP. So what's happened here is that the adenosine triphosphate has transferred its phosphoryl group, the final phosphoryl group, onto this glutamate. So that's right here. And now the next step, what happens is the ammonia comes in and it kicks off this phosphate. So the ammonia comes in and it displaces the phosphate. Now you have your glutamine. This is a positive charge, by the way. So now you have H3N plus C, COO minus. Now you have CH2, you have CH2, you have COO, and you have NH2. So what looks like a single-step process is actually a two-step process. Glutamate reacts with adenosine triphosphate to form this right here. So ATP transfers its phosphoryl onto the glutamate. Now, this is not a good leaving group, but now this is a good leaving group. Now ammonia can come in and displace this phosphate and attach where the phosphate is attached, and PI goes. So here you see the PI has left. ATP is converted to ADP plus PI. The hydrolysis, the energy of hydrolysis of ATP is used to drive this reaction, but it's happening this way. It phosphorylates, then something else happens. In the process of phosphorylating this molecule, changing it from this to this, I've actually invested energy into that molecule. I've raised the free energy content of this molecule to a higher level. Now it has more money that it can spend. In other words, now a nucleophilic substitution reaction can take place. Well, it's actually not nucleophilic substitution. It's happening at a carbonyl. But now a substitution reaction can take place. That's what's going on here. Okay, so